Welcome everyone to this lecture on separation and projection for convex sets. We're going to talk about an optimization definition of projection onto a convex set, and then also derive the fundamental property that really is the foundation of duality theory, that any closed convex set and any point that we have that's not an element of that closed convex set can be separated strictly from the convex set using a hyperplane. In another lecture, we'll then use the separation result to prove theorem of the alternative, which is really the essentially equivalent to strong duality for linear programming. But let's get started with what we have here. So first, we're going to give a geometric result about convex sets. So the idea is best illustrated by a picture. If I have a convex set and a point that's not part of the convex set, I can separate it with a hyperplane. And note that this is equivalent to saying that I can define a convex set using an intersection of half spaces. So more precisely, we can define any closed convex set by an intersection of half spaces. So what does that mean? Obviously, I don't have time in this lecture to draw all infinitely many half spaces that I would need, but you get the idea. So to write this out, what we're saying is that if C is a closed convex set, then C is equal to the intersection over all half spaces that contain C. And a simple picture will convince us that this is something special and specific to convex sets, certainly not true for non-convex sets. So, if we have a non-convex set, we have this point here. We cannot separate it from the convex set. This is our set C. We cannot separate this point from the convex set with a linear hyperplane, nor can we define this set by the intersection of half spaces that contain it. We would basically be adding this shaded region, this yellow region here, if we tried to do that. So here's what we actually want to prove. If I have a closed convex set, so if X is closed and convex, here's just a picture, but in pictures I have to make some decisions. Obviously I'm limited to drawing in 2 dimensions. I've drawn something that looks kind of like an ellipse, and in particular something that's bounded. So none of those things, of course, have to hold. So the theorem says that if X is a closed convex set and if Y is a point that does not belong in X, so here's Y, then there exists a hyperplane which leaves Y on one side and the set on the other side. There exists a vector C such that C transpose Y is strictly less than C transpose X for every X in my set, script X. And this is a strict inequality, and that's quite important. So note, if I didn't have strict inequality, it would be easy to guarantee this. I could just take C be the all the zeros vector. So this is the main result that we're going to prove in this lecture. Now, if we look at this picture, we already get the basic idea. So let's look at that idea from picture. Here's my point Y. Here's somewhere off here is my set X. And note that, at least as the picture is drawn, I have a closest point in X to y. And you can see that this closest point defines a hyperplane which seems to do exactly what is promised in the theorem. So this picture really is the idea that we're after. We're just going to make everything precise in this lecture. And the first thing that we need is the fact that there is this closest point. And you'll also note the way that I've drawn it, that this is exactly the Euclidean projection of the point y onto this convex set X. And indeed, we're going to start by giving an optimization definition of what projection onto a convex set means. And we're going to do it as follows. So, given y, not in the set X, because if it were in the set X, then the closest point would be itself. The distance would be 0. I want to look at the optimization problem, minimize y minus x. This is Euclidean norm. It doesn't matter that I square it. It doesn't make a difference. So what's important is that it's Euclidean norm and not something else. Subject to x belonging to this set X. And so this is exactly the picture from the previous slide. This is the closest point, and you can see that it really does correspond to orthogonal projection in this picture. We're going to see actually that this is exactly the case. Now, a first question you might have is, how do I even know that for a general closed convex X, closed and convex, how do I know that this optimal point exists? Certainly in the picture that I've drawn, it exists. And this is our first order of business. But we're actually going to appeal to a theorem from analysis called Weierstrass's theorem, which I'm not going to prove, which says the following. If I have any optimization problem, minimize or maximize, f of x subject to x in, let me give it a different name so it doesn't necessarily have to be our previous set. If f is a continuous function, and if omega is any closed and bounded set, then the minimum is attained at a specific point of omega. In other words, there exists some x star in omega such that f of x star is less than or equal to f of x for any other point x in omega. So what do we need to do to apply this to our situation? Well, we already know that we're closed. Note that convexity that has not yet appeared. We don't need convexity for this theorem. But we need to deal with the fact that x is not assumed to be bounded in our setting. But this is actually pretty easy to fix. So let's do this. Let's do this pretty quickly. So what do we know about x? Actually, I guess I should, to make sure that this is not a trivial result, we should assume in the statement of the theorem that it is non-empty. And it's not a very interesting result if x is empty. So let's show how we do this. So here's my point y that's not in x. Because it's not empty, we're guaranteed that it has some point w in x. I don't know what it is. I don't know if it's the closest point or not. And now let's look at the ball that's basically whatever this radius is. I'll use rho for radius. Let's look at the ball that's at least twice as big as that radius around w. Let's call this b2 rho. And a simple observation is that if I look at the minimization of y minus x, this is the Euclidean norm. I won't, if I don't denote it explicitly, such that x is in x. is equal to the minimum of y minus x, such that x is in the intersection of x and this ball. In other words, this minimum point has to lie somewhere inside of this ball, because any point outside is farther than w itself. So it's a simple result to show, but basically this means that I only need to worry about bounded sets. The ball is closed and bounded, x is closed and convex, and therefore the intersection is closed, convex, and bounded. So we can assume without loss of generality we'll just assume that x is not just closed and convex. This is what we had assumed before, but the key thing is bounded. This is what our additional assumption is without loss of generality. So now let's explore one of the important geometric properties of projection. So first of all, the fact that the minimizer exists allows me to define the projection onto x of a point, of any point y, to be the argument of this problem. Y minus x, Euclidean norm squared, subject to such that x belongs to my set x. So in other words, if this is y and this is my set x, then this point here I'm denoting as, with this notation, projection of x onto y. So we have used optimization and not some other property of projection in order to define this. So what do we notice from this picture? We notice that for any other point x, in my set x, this angle here is obtuse. It's greater than 90 degrees. Greater than or equal to 90 degrees. It would be, you can think about when it would be equal. So let's prove that what this picture is showing us is exactly what happens. I'm going to write this as a proposition. For everything as above, for any x in x, let's actually name this point here v star so that I don't have to keep writing px of y. It'll be a little more convenient to just write v star, but v star is a function of the set and also the point y that's not in there. For any point x in x, this angle that's made is obtuse. And what does that mean? That means that v star minus y transpose times v star minus x is non-positive. So this proposition is saying exactly what the picture is showing. So let's give this proof. So note that by convexity of the set x, for any lambda, lambda times x plus 1 minus lambda times this projection point, v star, this is also going to be in x, right? Just like the picture shows. So this line segment here is the mapped out by looking at lambda in 0, 1. Now I'm going to use the definition of v star as being the solution to the optimization problem. So what does that tell me? That tells me that y minus v star, this distance, always Euclidean norm, is certainly no greater than the distance between y and any other point in x. Which point am I going to take? Well, this point right here. So let's write that down. Y minus lambda x plus 1 minus lambda v star. And now I'm just going to expand this and see what we get. So this is equal to y minus v star minus lambda times x minus v star squared. And now just expanding the square, I get that this is now equal to y minus v star. You can see that I have the same thing on the left-hand side, so that is going to cancel. Minus twice lambda times y minus v star transpose x minus v star plus lambda squared times x minus v star squared. So what do we see here? So first of all, this cancels. Now, if we want, we could divide by lambda and see what happens when we take lambda to 0. It's the same as just noting that the second term is quadratic in lambda, and the first term is linear in lambda. So by taking, since this has to hold for all lambda greater than or equal to 0, this is equivalent to saying that this implies that this term here is less than or equal to 0. Y minus v star transpose x minus v star is less than or equal to 0. But this is exactly what we're trying to prove. So note I just flip both of these. And so this is equivalent to what we want to prove. V star minus y transpose v star minus x is less than or equal to 0. This is exactly what the above picture is showing. And now we're finally ready to prove the separating hyperplane theorem. Let's draw our picture again. Here's y. Here's my set x, somewhere off here. Here is the point v star, or if you like, projection of y onto x. And we can see just from this picture what we need. So let's let c, the vector that we're trying to find, let's let c equal v star minus y, just like I have in the picture here. And we want to show that c transpose y is strictly less than c transpose x for any x in my set x. So first, let's note that this holds for the point v star. So first, note that c transpose y is strictly less than c transpose v star. How do we see that? Basically just by direct calculation. So in other words, this inequality, this is equivalent to just writing out what c is. V star minus y transpose y is less than v star minus y transpose v star. This is in turn equivalent to just expanding this out, v star transpose y minus the Euclidean norm of y squared being less than the Euclidean norm of v squared minus v star transpose y. And now I'm just going to bring everything onto the right hand side and note the and basically form the square. And so this is exactly equivalent to 0 being strictly less than v star minus y squared, which indeed holds because we'd assume that y is not in x, and hence v star minus y is strictly positive. Okay, so we're satisfied that this holds, and now we're just going to apply the inequality that we proved, the key definition of Euclidean projection, namely that this angle is greater than 90 degrees. So for any x in my set x, c transpose x is equal to c transpose, I'm just going to add and subtract v star minus v star minus x. This is equal to c transpose v star minus c transpose, I'll write out what c is again, v star minus y transpose v star minus x. We know that c transpose v star is greater than c transpose y, and we can just stop there because v star minus y transpose v star minus x, flipping back, is exactly something that's less than or equal to 0. So I'm subtracting something that's less than or equal to 0, hence adding, hence only making this side even bigger. And so therefore this is greater than or equal to C transpose Y. Strictly greater than C transpose Y, because C transpose V star is strictly greater than C transpose Y, and this term here, and the second term is non-negative. So this concludes the proof of the separating hyperplane theorem. We have a closed convex set, a point not in that set. There is a linear hyperplane so that C transpose Y is strictly less than C transpose X for any X in the set.